So let's take a look at a couple examples of this. So in this first example, we have an object that's traveling 6 meters north in 3 seconds. And the first thing we want to find is the average velocity of this object. So what I like to do is I like to make just a little give and find chart. So I know what I'm given and what I need to find. So I know what I'm given. I'm just going to change the pen stroke here. Is the displacement. We know the displacement is 6 meters. And it's to the north, which we'll ignore just for now, but we know it's displacement because it's given direction too, and the time is 3 seconds, and we need to find the velocity. So, an object travels 6 meters north in 3 seconds, so average velocity, we can use the formula displacement over time. You know the displacement is 6 meters over 3 seconds, and we keep the units meters per second, but we reduce to 2 meters per second. 2 meters per second. So now what we want to find is the instantaneous velocity of this object at 2 seconds. So what we're going to do is we're just going to look over here, and we're going to put a point at what we know. It's 6 meters over 3 seconds. So this is what will be a position time graph. So this is going to be position, and this is time. So position in meters, time in seconds. And because it takes 3 seconds to travel 6 meters, I need to draw a line that connects these points. So I'm just going to not kid myself and try to use a straight line tool here. So right at this 6 seconds, I'm going to draw a line that connects me right through to 0. So here's my slope here. Now I want to find the instantaneous velocity of this object at 2 seconds. So what I can do is I can look at 2 seconds and see where this crosses, and it's traveled 4 meters in 2 seconds. So I know that the displacement is 4 meters after 2 seconds, which means that the instantaneous velocity at 2 seconds, if we reduce this, is 2 meters per second. Which is the same as above, and will be the same as any slope on this graph, or any 2 points on this graph, because the object is moving in uniform motion. And because the velocity is constant, no matter where you look on this graph, it's always going to be going 2 meters per second. So the instantaneous velocity is all you can find at any point on the graph and by any point on the slope, because if it's constant, it's always going to be the same. And a second example, object again is traveling in uniform motion. This time it's 5 meters per second to the right. So again, we're going to the right. It's a positive direction, and we know its velocity. And we want to find the displacement of this object after 10 minutes. So first things first, and that is careful of units. We're given minutes, and we want to find the displacement. We're given velocity in meters per second, 5 meters per second, but we're given displacement after 10 minutes. So time, we want to convert to seconds. So let's do a quick unit conversion. It's 10 minutes times 60 seconds per minute. Cancel out minutes and minutes. So 10 times 60. So we know the time is 600 seconds. So so it's going 5 meters, 600 seconds. We want to find the displacement. So if you remember from before, from our little velocity triangle, the t. If we want to find the displacement, we can multiply the velocity times the time. So we know that displacement equals velocity times the time. That means it's 5 meters per second times, since it's 10 minutes, it's 6 600 seconds. So you multiply that together, 5 meters per second times 600 seconds gives you 3,000 meters. And again, because it's traveling to the right, and we want to find the displacement, we want to make sure that we give it a direction. So 3,000 meters right. Or plus 3,000 meters. It's a positive direction. So in this case, we want to find the displacement of this object after 3 seconds. So if we want to represent this graphically, remember we can make this on a graph, and we can find displacement on a velocity time graph. So we know this object is traveling at 5 meters per second, and that's uniform motion. So all we have to do is we need to take a line at 5 meters per second and just draw it straight across. Straight across there, or as straight across as I can get it. Not the most straight line, but we get the idea that it's constantly traveling in this 5 meters per second line there, and that just made it worse. So if we're going to find the displacement of this object, remember we can just take the area underneath this graph, and we want to find it after 3 seconds. So if I look at the area between the velocity being 5 meters per second and the time being 3 seconds, all I have to do is find this area underneath the graph here. And this area will be my displacement. So this area is 5 meters per second up, times 3 seconds across, which gives me an area of 15 meters. Seconds and seconds cancel out, so the area under this is 15 meters. And again, this is just analogous to saying the displacement equals the velocity multiplied by the time. So that's 5 meters per second times 3 seconds, which gives us a displacement of 15 meters right, as this object is still traveling to the right. So that's it for today. Please try the practice examples in your book, and read your SNAP notebook if you need any further clarification on this subject. We'll see you guys next time.